Hello, honors chemistry students. I'd like to examine a different type of stoichiometric problem today in which you are required to convert moles of reactant to mass of product. This is one of the quintessentially classic stoichiometry problems that you're going to face throughout your chemistry course. With that being said, let's take a look at the specific problem, in which you're required to calculate the mass of barium carbonate produced when an excess of CO2 is bubbled through a solution containing 0.205 moles of barium hydroxide. As always, I want you to approach the solution to this problem using the known, unknown solution style of problem solving, which is a core standard for honors chemistry. The best place to start is to actually examine the chemical reaction involved. So you're told that you're going to be reacting barium hydroxide, which is a base, which in all probability will be aqueous in solution. And to that, you're going to bubble carbon dioxide gas through the solution to produce a precipitate called barium carbonate, which is a white precipitate, by the way, which will be a solid substance plus water. That being said, water is an unionized substance, which is a liquid. This looks or appears to be a balanced reaction in which you have one atom of barium on both sides. You've got 4 atoms of oxygen on the reactant side, 4 atoms of oxygen on the product side, 2 atoms of hydrogen on the reactant side, and 2 on the product side. So quintessentially in this problem, you're asked to calculate the mass of barium carbonate produced. So in the unknown section, I want you to write mass of barium carbonate, and typically mass is expressed in grams. So somehow you have to calculate how much barium carbonate is produced in a solution that contains a given number of moles of reactant, which in this case, we know that there are 0.205 moles of barium hydroxide in solution. And you're told that CO2 is in excess, which means that the barium hydroxide is going to be what we call in the trade the limiting reagent. That is the substance which limits how much barium carbonate you can produce. So in essence, we're looking for the grams of barium carbonate. That's one way to set this up, but I like to embellish this a little bit more by saying the following. We know that you're given a given number of moles of barium hydroxide. So you're given a given number of moles of barium hydroxide, which is 0.205 moles of barium hydroxide. You know CO2 is in excess. And the other thing you have to consider in terms of your solution is that you're going to be converting moles of barium hydroxide, which you're given in the problem, to moles of barium carbonate, and then from moles of barium carbonate to grams of barium carbonate. So we've got 2 different conversions that you are required to do to solve this problem. To go from moles of barium hydroxide to moles of barium carbonate, you need to look at the stoichiometric ratio between barium hydroxide and barium carbonate, in that there's 1 mole of barium hydroxide consumed to produce 1 mole of barium carbonate. So we're going to use that relationship of the stoichiometric ratio as a bridge between moles of reactant to moles of product. And then to go from moles of product to grams of product, you're going to need to calculate the molar mass of barium carbonate. Since that's an ionically bonded substance, we're going to refer to that as the gram formula mass of barium carbonate. So we've got an extra calculation that you need to do to solve this problem. But that means you need to know the gram formula mass of barium carbonate. To do that, you need to know the gram atomic masses of barium, of carbon, and of oxygen. So if you look those up on your periodic table, you need to know the gram atomic mass of barium, which happens to be 137.33 grams of barium per mole of barium. And you also need to know the gram atomic mass of carbon, which is 12.011 grams of carbon per mole of carbon. And you need to know the gram atomic mass of oxygen, which is 15.9994 grams of oxygen per mole of oxygen. So armed with those three pieces of information, you should be good to go with predicting how much barium carbonate you can produce. Before you can do anything, the first thing you're going to need to do is to calculate the gram formula mass of barium carbonate, which is one of the skills you learned in the last section on chemical quantities. So you're looking for the gram formula mass of barium carbonate, which is expressed in some units of grams of barium carbonate. You know that 1 mole of barium carbonate formula units has 1 mole of barium. So there's 1 mole of barium in that compound, and you want to convert moles of barium to grams of barium. The gram atomic mass is an excellent vehicle to do that. Keep in mind that whatever unit you want to get rid of goes in the denominator, and whatever unit you want to achieve goes in the numerator. So we'll set our conversion factor up in that fashion. Moles of barium cancel, and you're left with grams of barium. Next, you have to consider how many moles of carbon you have in barium carbonate, which in effect you have 1 mole of carbon. So you know that compound contains 1 mole of carbon atoms, and you know that carbon has a mass of 12.011 grams of carbon per mole, 1 mole of carbon. Again, moles of carbon cancel, and you're left with grams of carbon. Lastly, barium carbonate contains 1 mole of barium carbonate formula units contains 3 moles of oxygen. So you know there are 3 moles of oxygen, and you know that each mole of oxygen has a mass of 15.9994 grams of oxygen. Moles of oxygen cancel, and you're left with grams of oxygen. So I'm going to take out my calculator real quick, and we're going to look at this calculation. We know that we have 137.33 grams of barium plus 12.011 grams of carbon plus 3 moles of oxygen times 15.9994 grams of oxygen, which gives us a value of 197.3392. The value with the fewest number of decimal places is barium, so we're going to limit our gram formula mass to 2 decimal places. So this would be 197.34 grams. So we're going to write that over here and squeeze that in. We're going to have 197.34 grams of barium carbonate. Sorry about that. I'm running out of a little bit of space over here. But that is, in effect, your gram formula mass. Armed with that information, you should be able to convert from moles of barium carbonate to grams of barium carbonate. That being said, the second thing you're going to have to calculate, we're going to just go right after this to calculate the grams of barium carbonate produced, we're going to be looking for the mass of barium carbonate expressed in some units of grams of barium carbonate. Always start with the information you're provided with, because you're told that you have a given number of moles of barium hydroxide, which is 0.205 moles. So you know you have to start with a given amount of reactant. And you have to convert moles of barium hydroxide to moles of barium carbonate by examining the mole ratio between the reactant and the product. In this balanced chemical equation, there are no coefficients in front of each of our reactants or products, so it can be assumed that the coefficients are 1. So therefore, we want to eliminate moles of barium hydroxide, so we know that 1 mole of barium hydroxide is consumed to produce 1 mole of barium carbonate. That's what we call a 1-to-1 stoichiometric ratio. There may be those students who say, well, why do you have to divide 1 by 1? My response to that would be that this is not just about numbers, it's all about units. The units have to cancel. And you can see we've gone from moles of barium hydroxide to moles of barium carbonate, just like in our solutions pathway. The last step is to convert moles of barium carbonate to grams of barium carbonate. So we want to eliminate moles of barium carbonate and arrive at our answer in grams. That being said, that's the perfect opportunity to use the gram formula mass of barium carbonate, because we know that 1 mole of barium carbonate formula units possesses a mass of 197.34 grams of barium carbonate. Once again, moles of barium carbonate cancel, and we will be left with a unit in grams. Now you can see we have just a fraction of a mole of barium hydroxide. So we would expect this answer to be about a fifth of 197.34. Let's see if that works out. So we're going to multiply 0.205 moles of barium hydroxide times 1 times 197.34, and we arrive at an answer of 40.4547 grams of barium carbonate. Now when we look at that answer, we have to consider how many significant figures are in our measurement. Bear in mind that our measurement has a decimal point, so using the Atlantic Pacific significant figure technique, you draw an arrow through all the zeros coming from the Pacific, since the decimal point is present, until you get to the first non-zero digit. Every digit thereafter is considered significant, so we would say this measurement has 3 significant figures, which means our answer should only have 3 significant figures. Thus, the decimal point is present there. You draw an arrow from the Pacific until you get to the first non-zero digit. The first 3 digits are considered to be significant. So the 4, the 0, and the 4 is significant. However, we can drop the 5 and round the 4 up to a 5, so our answer works out to be 40.5 grams of barium carbonate. And that answer makes sense because 40.5 is approximately 197.34, because we really have about a fifth of a mole of barium hydroxide. So in that way, we are able to convert moles of a reactant to moles of a product using the stoichiometric ratio, and then predict the mass of product required by using the gram formula mass. And that's how you convert moles to mass. So therefore, we refer to this problem as a mole mass problem, because you're converting moles of reactant to mass of product.